Alrighty, good morning, lads and ladies. Welcome back to MAP2302. Today we're going to explore the Laplace transform a little bit more. I'm going to show you how to take the Laplace transform of a bunch of different functions. We're going to talk a little bit about convergence. We're going to have some fun with complex numbers. That's always awesome. And then I'll show you some other features of the Laplace transform, some kind of ways the Laplace transform behaves algebraically. I don't necessarily think we're going to get to solving any differential equations with the Laplace transform today, but that will be the big payoff here. The main idea is that the Laplace transform allows you to take a constant coefficient linear differential equation and basically turn it into a partial fractions problem, which is pretty cool. But in order to get there, you need to be able to take the Laplace transform of quite a few different functions. You need to be able to take inverse Laplace transforms, like I give you the Laplace transform and tell me what function that came from. And you need to know how to take the Laplace transform of a kind of generic derivative. And that's really it. So with that said, I think we're about ready to get started. One other thing I wanted to share with you guys. So I know that yesterday's lecture got a little bit stumbly when we talked about the substitution in the Cauchy-Euler equations. So I did go ahead right after class yesterday and put this together. I had confused myself a little bit, thinking that we were making a substitution for a dependent variable, when in fact we're making a substitution for an independent variable. But this is good. I reviewed the video and made sure everything is pretty much kosher. Other links here. Here's the kind of Patrick GMT index on power series. I think you may find this stuff useful if you're a little bit uncomfortable with power series. And the Paul's online notes, kind of differential equations, power series review. So Paul has a whole separate thing on power series. If you want to go back and kind of go back over all the stuff that you're supposed to learn about power series, this is just the stuff which is essential for differential equations. But I touch on both of those things in this video. So this video, we do the substitution, then I briefly review some concepts from power series, and then prove that Euler identity, the e to the I x equals cos x plus I sin x identity. So if you guys don't mind, we're going to get moving here. I am going to refresh my coffee, and then we'll dive into more with the Laplace transform. One other thing, I've decided to make a little change in notation. So rather than using x for my independent variable and all this Laplace transform stuff, I am going to use t. It's the normal thing to do. So we've kind of suppressed this throughout the semester, but 90% of differential equations, the variable is time. Out there in the real world, in the application problems, pretty much always you're looking at how some system, some physical system evolves over time, right? Like the mixing problem or the temperature problems, population problems. And because the Laplace transform is so often used in the context of application problems, I think it's healthier to use the variable t. Your textbook sometimes uses x, sometimes uses t, but reviewing all the sections of the Laplace transform mostly uses t. So we're going to do that. Today is the 28th of July, 2021. I don't know if you guys saw, the CDC updated their guidelines for masks. I guess due to the Delta variant, they're recommending that in public spaces, everybody wear masks. Indoor public spaces, people wear masks again. It's a little disappointing, if you haven't gotten vaccinated yet, please do so. Help us move forward from this thing. If people were as vaccine skeptical about polio, we'd still have children dying of polio. That's as political as I get, I promise. All right, so recall. Today, we'll start, Laplace transform. One thing I said yesterday that I was a little bit uncertain of, Laplace and Cauchy were contemporaries. That's true. That's true. Laplace and Cauchy, two famous French mathematicians, were alive and working around the same time, both a little bit after Euler's time, although they were born before Euler died. So yeah, recall. Given a function f of t, the Laplace transform of f of t is the new function let's see, L. And then sometimes they use curly braces, sometimes parentheses, sometimes square brackets. It's a script L. And this is defined in terms of the improper integral, the integral from 0 to infinity, f of t e to the negative st dt. And fun vocab, the e to the negative st part here, this is called the kernel. So if you study other integral transforms like the Mellin transform or the Fourier transform, you'll come to appreciate the significance of the kernel of an integral transform. Basically, the idea is that it's kind of like f of t are the coefficients of a power series. That's basically the idea. So what a power series does, one way of thinking about it is it takes in a sequence, an, and it spits out a function, f of x. And the an's, each one gets multiplied by x to the n, or x minus a to the n. Each one gets multiplied by some power of a variable, and then you add all those up. And that gives you some new function whose variable is not n, but x. Sort of the same thing going on here. But it's a continuous analog. So every output value from the function f is getting multiplied by e to the negative st, and then added up over the whole domain of f, right? From 0 to infinity at least. So it's very, very similar. The f of t's here are doing the same sort of thing that the an's do in power series. And one consequence of that is that the output is not a function of t. We usually use a capital F, and the variable is going to be s. And last time, we calculated the Laplace transform of the function 1. And we saw that that was 1 over s. But this only works if s is positive. Kind of like how we say sigma x to the n is 1 over 1 minus x, but only if the absolute value of x is less than 1. Same sort of thing. Today, I want to calculate a handful of other Laplace transforms. We're going to do sines, cosines, exponentials. We're going to prove that the Laplace transform is a linear operator in the same way that the differential operators are linear. And we'll talk a little bit about inverse Laplace transforms. Okay, let's do it. So I think the next thing to do, probably, tuck this in our pocket. Constants. The building blocks for polynomials are integer powered power functions. So we can look at one or two of those, other big important things, sines, cosines, exponentials. Since we've already done one, and that's sort of a power function. Let's see if we can find the Laplace transform of t itself. T squared. See if we can get an idea of the Laplace transform of t to the n in general. So I'll do like t, and then maybe jump straight to t to the n. And then we'll prove linearity. So L of t, the Laplace transform of the function t, would be the integral from 0 to infinity of t e to the negative st. Who can help me with this integral? If we're being careful, and I do want to be careful here, what's the very first thing I should do if my aim is to evaluate this improper integral?
Well, it's just an integration by parts, correct?
It's true that the antiderivative step is integration by parts. But even before then, there's something that I'd like to do, and that's to express it as a limit of Riemann integrals. Because right now, remember, this is not a Riemann integral. This is something analysts get very picky about. And that word careful is what when I tell you, for example, on the next exam, to carefully calculate the Laplace transform, I mean, I want to see this step. I want to see you go from integral 0 to infinity to lim r to infinity integral 0 to r. Because it matters. The limit at the end requires some love. And if this integral were to diverge, then the antiderivative is meaningless. And then what Cody said is correct. This is an integration by parts problem. So here I would pick u to be t and dv to be e to the negative st. du is dt, and v is negative 1 over s e to the negative st. So here I'll get lim r to infinity. Open up a big bracket right here. And then we'll have u times v evaluated from 0 to r. So that's t times negative 1 over s e to the negative st. R, that is negative t e to the negative st over s. And this is evaluated from 0 to r. Minus the integral from 0 to r of v du. So that minus and this minus are going to make a plus. I've got a 1 over s e to the negative st dt. Close that. Okay. So remember, when you're doing integration by parts with a definite integral, you need to evaluate the u times v piece that gets spit out between your bounds also. And don't wait until the end to do that. It's not just ugly notation, it's wrong. So we'll crunch this guy, and we'll plug in 0 and r for t here. Remember, these are t values. Because that's the variable we're integrating with respect to. All right, I'm going to jump this over here so I have a little more space. Lim r to infinity. And then here, I'll do my evaluation. So this is going to be negative r e to the negative sr over s, and then minus what we get when we plug in 0. But when I plug in 0, this is 0 times e to the 0 over s. That's 0 times 1 over s, which is 0. So that's all we get there. From the remaining integral, I can pop out the 1 over s. So this is a constant because I'm integrating dt. And then the antiderivative of e to the negative st is negative 1 over s e to the negative st. And this piece now gets evaluated from 0 to r. Is everybody with me so far? So I guess I'll continue my diagonal downward trend here because we need still more space. We have lim r to infinity bracket negative r e to the negative sr over s. That's my first piece. And then minus 1 over s squared, these two, times this thing evaluated from 0 to r. So I'll write that as e to the negative sr minus e to the negative s times 0, which is e to the 0, which is 1. So we've got some limits to manage. This is sort of the easiest limit here to manage. What is e to the negative sr doing as r gets bigger and bigger and bigger and bigger?
Zero.
Yeah, as long as s is positive. So this piece will go to 0 as long as s is positive. If s is not positive, then this piece would blow up to infinity, right? If s was, I guess I could say greater than or equal to 0 here. But yeah, if s is negative, then this is like e to the negative negative 2r, which would be e to the 2r, and that blows up. But if s is positive, then this is like e to the negative 2r, e to the negative 5r, that would go down. This piece, remember the s downstairs here is constant. What does this piece do and why?
We'll go to positive infinity, correct? Or would it go to negative infinity?
So the r piece on its own here, this would go to negative infinity. And e to the negative sr, we just said that goes to 0. So this looks like zero times infinity, or infinity times 0. And what does that tell us? Remember Calc 1?
It's undetermined.
Yeah, it's an indeterminate form. So we need to carefully handle the limit as r goes to infinity, negative r e to the negative sr. And we're going to assuming s is positive, because I need s to be positive for the other piece to go to 0, right? To avoid this other piece going to infinity, which would fuck the whole thing up, I need to assume s is positive. So in this calculation, I'll also be assuming s is positive. Right. This is the one that we need to calculate. This is lim r to infinity, negative r over e to the positive sr, right? E to the negative blah is 1 over e to the blah. And now the top looks like a negative infinity over positive infinity. So this, sorry, negative infinity over infinity. So what can I do with that?
L'Hopital's rule.
Very good, L'Hopital's rule. So what does L'Hopital's rule say?
If we differentiate the limit of the differentiation will be the same as the limit of the original equation.
That's the idea, yeah. Specifically, if I differentiate the top and bottom on their own, then I can try again. So L'Hopital's rule says if lim x to c f of x over g of x looks like 0 over 0 or infinity over infinity, then lim x to c x over g of x is the same as lim x to c f primed x over g primed x. So we differentiate the top and bottom separately. As long as we have an indeterminate ratio, that will be the same as the original limit. So here, if I apply L'Hopital's rule, and I just like to put a little L over my equal sign to indicate I'm using L'Hopital's rule, then I get lim r to infinity derivative of negative r is 1, derivative of e to the sr is s e to the sr. And now this is negative 1 over infinity, which is 0. So the purple piece here goes to 0. And this piece here, the blue piece, goes to 0. So now we can come back in and say what our result is. Are there any questions on the limit work here? All right, you will have to do this on the test. There will be points on the test lost if you don't carefully handle your limits. So it's not at all inappropriate to ask questions.
Is there any case where it is a positive SR?
Well, because the kernel of the Laplace transform is e to the negative SR, that's the thing that kind of tends to show up all the time. But yeah, we can imagine ways to manipulate the function f such that the exponential has a different power. I'll be showing you a couple examples of that a little later. But kind of the idea is that that e to the negative SR, that kernel, goes to 0 really fast. And that helps drag down whatever function f you put in there. And that's what helps that integral converge. If the kernel didn't go to 0 super fast, then it would be hard for the transform to output useful things, no more limit, for the vast majority of functions. So having that kernel go to 0 helps the integral converge, even if you plug in a function f that grows kind of quickly or doesn't go to 0 itself. I'll be real quantitative about that in just a minute. All right, so our limit is now gone. We've calculated the limits. This first piece is 0, and this is minus 1 over s squared times 0 minus 1. So this is just negative 1 over s squared times negative 1 is 1 over s squared, i.e., I'll use this other notation. We'll practice this. If f of t is t itself, then capital F of s, the Laplace transform, is 1 over s squared. That is the Laplace transform of f of t equals t. You could write this as script L of t equals 1 over s squared also. Okay, time for some comparisons. If you look at these two calculations we've done, the Laplace transform of 1 is 1 over s. The Laplace transform of t is 1 over s squared. Remember, the other way of writing this would be L of t equals 1 over s squared. That's the way that's analogous to what we have above. So we may approach a conjecture at what the Laplace transform of t to the n is, right? This is t to the 0. That gives us 1 over s. This is t to the 1. That gives us 1 over s squared. We begin to think maybe that the Laplace transform of t to the n is something like 1 over s to the n plus 1, or has an s to the n plus 1 downstairs. And it turns out that the 1 is not correct. Turns out that we do get other terms upstairs. but it's proportional to 1 over s to the n plus 1. That's the good news. In general, what you're going to get upstairs is a factorial. So the truth is that L of t to the n is n factorial over s to the n plus 1, where n factorial, you all remember, I'm sure, is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. It's the product of all the positive integers less than or equal to n. We can prove this without too much work using integration by parts and a little bit of hand waving. And so let's go ahead. Let's prove this. So L of t to the n would be the integral from 0 to infinity. And I might be a little bit sloppy on this one, a little less careful. T to the n, e to the negative st dt. No, maybe not, maybe not. We should model good behavior for you, right? So let's do that. Lim r to infinity, because there are some subtle limits here. Integral 0 to r, t to the n, e to the negative st dt. The big deal is that integration by parts is technically illegal on this, but is legal on this, because again, Riemann integral, not Riemann integral. The IVP, I'll do it over here this time, so I need many of them. U is t to the n, dv is e to the negative st, du is nt to the n minus 1, v is negative 1 over s e to the negative st. So I'm going to get here lim r to infinity u times v, so that's negative t to the n over s e to the negative st minus the integral of v du. So that's pop all the things out. The minus minus will make plus. I'll have n over s and then integral 0 to r. Oh, I need my evaluation bars here too. 0 to r. Integral 0 to r t to the n minus 1 e to the negative st. Now here's a cool thing. We could use induction just for fun. How many know what mathematical induction is? Give me a react in Zoom if you're familiar with the concept of mathematical induction. Thumbs up, whatever. Okay. Basic idea behind induction is if I tell you that if it rains on a given day, it will rain on the day that follows. Right? So raining on one day implies raining the next day. I'm able to prove that to you. And then additionally, I tell you it rained today. What could you deduce?
That it will rain tomorrow.
It will rain tomorrow. But also, if it rains on a given day, it will rain on the following day. So if it rains tomorrow, it would rain the day after that as well.
So it rains forever.
Right. Yes, very good. Exactly. It would rain every day from hereafter. That's induction. So an induction proof goes like this. First, you prove a base case. That's like it rained today. Then you prove the implication. If it rains on a given day, it will rain on the day that follows. You prove if the statement is true for some value of n, then it must be true for the next value of n. So the truth of the statement for one value implies truth of the statement for the next value. Those two things, statement is true for some particular value of n, like n equals 1, and statement is true for a given value implies statement is true for the next value. Those two things together show that that statement is true for every integer n. That's induction. So let me show you how I'm going to use induction here. I do need to calculate some of these limits. here this negative t to the n over s e to the negative st. If I evaluate that between bounds, when I plug in 0, the t to the n makes everything 0. When I plug in r, I'll have negative r to the n over s, and then I'll write the e to the rt downstairs. Right, e to the negative rt is e to the rt downstairs. And then here I have plus n over s. And then with this guy, I'm going to rewrite this as an improper integral. This is integral 0 to infinity. T to the n minus, oh, I left off my dt. T to the n minus 1, e to the negative st. T. And you recognize this as the Laplace transform of t to the n minus 1. All right, you take your definition of the Laplace transform and just swap that n for an n minus 1, you get this. The piece over here is going to go to 0 by n applications of L'Hopital's rule. So, I don't have the time to write out n applications of L'Hopital's rule. The truth is it would be another inductive proof. This goes to 0 by n applications. And this is the Laplace transform of t to the n minus 1. So the Laplace transform of t to the n, let me is equal to n over s times the Laplace transform of t to the n minus 1. Let me come back up here to the factorial thing in blue. Another way of defining the factorial function, if you haven't seen this before, is to say that n factorial is equal to n times n minus 1 factorial. This, together with the definition 0 factorial equals 1, defines the factorial function in the same way that the above definition does. You'll notice the functional equation here is identical to the functional equation here. I've just got an n over s instead of an n. So this implies say this, which implies if I want to knock this power down again, the n minus 1, that exponent is going to pop out here and another copy of s downstairs. So maybe here, I'll go ahead and let's do this. This would be n times n minus 1 over s squared times the Laplace transform of t to the n minus 2, and so on. So every time I bring this power of t down by 1 inside the Laplace transform, the old power shows up out here, and we get another copy of s downstairs. Each one of these equalities is another run of integration by parts. This is an induction proof. I'm not doing it super formally because the formal steps would be even more confusing, I think. So what all this implies is that the Laplace transform of t to the n is the thing we thought, right? Every time you knock this power down by 1, next time you get n minus 2 over s cubed. So n times n minus 1 times n minus 2 all the way down, that's n factorial. And if I multiply s by itself n times, that's s to the n. So that's the Laplace transform of t to the n. Cool stuff, right? Improper integrals are awesome. Integral transforms are awesome. You'll see this is consistent with our previous two calculations. Just remember that 0 factorial is 1. That's a thing people sometimes have issues with. Next. This is a big deal. The Laplace transform is linear in the sense that if I want to transform a sum of two functions, it's the sum of the transforms. So I want to find the Laplace transform of, t plus t cubed or something like that. Find the Laplace transform of t, find the Laplace transform of t cubed, add them up. And the Laplace transform of a constant times a function is equal to that constant times the Laplace transform of the function. So I hope you realize that the things on the page are exactly what you need to calculate Laplace transforms to polynomials. If you know how to find the Laplace transform of any power of t, and you're allowed to split up Laplace transforms over addition, and you're allowed to pop out constants, then the Laplace transform of 3t to the 5 minus 2t squared plus 17 minus 8 is going to just be split it apart, transform each piece, and call it a day. Proof. This is not a hard proof at all. It's easier than the thing we just did. I'll number these as 1 and 2. So to get 1, just write out what L of f of t plus g of t is. It's the integral from 0 to infinity of f of t plus g of t times e to the negative st dt. And one of the things we proved back in Calc 2 is that improper integrals are linear. Now you could write this out as a limit, but we actually did prove that back in Calc 2, that the improper integral of f plus g is the improper integral of f plus the improper integral of g. So all you really have to do is distribute in here. So within my improper integral, I will distribute that e to the negative st. I get integral 0 to infinity f of t e to the negative st plus g of t e to the negative st dt. And that is integral 0 to infinity f of t e to the negative st dt plus integral 0 to infinity g of t e to the negative st dt. And that's it, you're done. This is the Laplace transform of f of t. And this is the Laplace transform of g of t. So we've proved one. Similarly, Laplace transform of a constant times f of t is the integral from 0 to infinity constant times f of t times e to the negative st dt is constant integral 0 to infinity f of t e to the negative st dt, which is that constant c times the Laplace transform of f. Done. So yeah, Laplace transform is a linear operator. So not only do we now know how to transform any polynomial right? Just by taking the transform of each piece on its own, popping the constants out along the way. We could also combine any functions who we know the Laplace transform of and get the Laplace transform of those. So the only thing to do from here is to kind of further expand our library of known Laplace transforms. I'm going to show you how to do e to the at, sine t, and cos t. And that, I think, will kind of complete our library for now. And the sines and cosines are fun. They can be done horribly, but they can also be done very cleverly. And I will do it cleverly for you. Okay, so super duper important stuff here. Laplace transform of t to the n, linearity. Kind of everything we've done so far is encapsulated in these two boxes. It's a meaningful amount of work, but the Laplace transform is a big machine, so that's what we expect. Cool. Make sure you have these nice and clear in your notes.
Can I see the bottom, please?
Sure. So here was the sort of end of that proof. To get the constant times Laplace transform, we just wrote down the integral. And then the big step is here to here, right? Here to here is where we use the fact that the integral is a linear operator. That's what this all relies on, right? The Laplace transform is linear because the integral is linear, and this kernel is not horribly badly behaved. In fact, this would work with any multiplicative kernel. So it really does come down to the fact that the integral is itself a linear operator. Split the integral up over a sum, pop a constant out of an integral. And if you can do those things, you can do it with the Laplace transform.
Okay, thank you.
So two more important families of functions. You could say three if you wanted, but like e to the at, and then sines and cosines. Sines and cosines really kind of one thing, really kind of both actually exponentials. So let's do it. The Laplace transform of e to the at is the integral from 0 to infinity, e to the at, e to the negative st dt, which is the limit, we're going to do these carefully, limit r goes to infinity, integral 0 to r, and then e to the at times e to the negative st, you multiply like basis, so you're adding the exponents. This is e to the at minus st, which is e to the a minus s times t. So inside doing algebra, outside writing the improper integral as a limit. So this is lim r to infinity. Antiderivative for e to the a minus st is 1 over a minus s times e to the a minus st evaluated from 0 to r. The 1 over a minus s, this piece is a constant with respect to the limit. The limit is in r. The evaluation bracket here is in t. So the a and the s are both constant with respect to the two calculus operations going on. So he'll come out 1 over a minus s times lim r to infinity. And then I'll plug in r for t and 0 for t. And I get e to the a minus s times r minus e to the a minus s times 0, which is just 1. And again, I have to ask, for a limit of something that looks a little bit like this as r gets bigger and bigger and bigger. So we know from experience, we're hoping that this piece goes to 0. What are the conditions on S that will allow this piece to go to 0 as R goes to infinity?
The absolute value of S is greater than A.
It's an interesting requirement. I think we don't need any absolute values. I think what I need is that this exponent is negative. And so I think what I need is A minus S to be negative, but you're on the right track. So this piece here will go to 0 as long as A minus S is less than 0, which is equivalent to saying add S to both sides, A is less than S. So S needs to be bigger than A, i.e. S is bigger than A. So this piece is going to go to 0. So my whole Laplace transform is 1 over A minus S times 0 minus 1, or negative 1 over A minus S. And this negative can be thought of a few different ways. The nicest way to do it is to say, well, really, let me bring that negative downstairs. Negative parentheses A minus S is S minus A. So this is 1 over S minus A. And again, only defined for S strictly greater than A. So that's your Laplace transform of the exponential function. Laplace transform of e to the a s is 1 over S minus A. Yeah, S has to be bigger than A. You need S minus A to be positive. Right, S to be negative. Oh, sorry, e to the at. Holy shit. So many symbols to juggle. Yeah, the function we are transforming is e to the at. Okay, so now any sum of polynomials and exponentials we could handle, and that implies we know how to handle hyperbolic trig functions, right? Because hyperbolic trig functions are like 1/2 times e to the, x, or e to the t plus e to the minus t. So you can pop out the 1/2 and then transform e to the t, subtract the transform e to the minus t, both of which would come from this formula. But the regular trig functions, just good old sine at, cos at, we don't know how to do those yet. And I am going to do something sneaky that uses linearity and complex variable theory a little bit, because it's going to save us a lot of time. Speaking of time, how much do I have left? 10:32. We're doing good. Okay. Sines and cosines. So I'm going to call it sine at cos at. If you haven't watched that video I posted yesterday, I encourage you to watch it because you'll understand the Euler formula, e to the ix thing, much better. And I'm going to use that here. Before I do that, so kind of a prereq, the complex number alpha plus I beta is said to have real part alpha and imaginary part beta, denoted re alpha plus I beta equals alpha, and m alpha plus I beta equals beta. Right, so the piece that's attached to the I, we call that the imaginary part. The piece that doesn't have an I, we call that the real part. And there's notation for this. You can think of the re function as a function that takes in a complex number, spits out its real part. And the im function takes in a complex number, spits out its imaginary part. Very simple functions. You'll notice that alpha plus I beta is a linear combination of alpha and beta. All right, so let's say here now, since e to the IAT by our Euler formula is the cosine of AT plus I times the sine of AT. We have re of e to the IAT equals cos AT. And im of e to the IAT equals sine AT. I'm sorry, this is a times t. I don't know why I wrote a to the t. So what I'm going to do is find the Laplace transform of e to the IAT, then take its real and imaginary parts. The real part is the real part of the Laplace transform of e to the IAT will be the Laplace transform of cos AT. And the imaginary part of the Laplace transform of e to the IAT will be the Laplace transform of sine AT. This is a consequence of linearity. That's it. That's it. So you could start by writing cos AT plus I sine AT. Take the Laplace transform of that, split it up, you get Laplace transform of cos AT plus I times the Laplace transform of sine AT. But then in the other direction, say, oh, okay, that whole thing is the Laplace transform of e to the IAT. Crunch that out as an exponential, and then at the very end, take the real part, that's going to be your cosine transform, and the imaginary part, that's going to be your sine transform. Done and done. It's really beautiful stuff. And it's going to save us a lot of time, because if you want to take the Laplace transforms of these things kind of without using any complex variable theory, you need to do looping integration by parts. And not just regular looping integration by parts, looping integration by parts within an improper integral. It requires two applications of IBP and then kind of adding your integral back over. It's a lot of work. So it's a lot of work. Arthur Maddock from MIT calls it a hack. It's not a hack, and it's a good method, but it's not as smart as this. So we're going to use this. And we're going to bravely calculate the Laplace transform of the complex exponential e to the IAT. At the end, there will be a little bit of algebra, but I promise you it's nothing too bad. All right, we all okay with the roadmap here, the plan? Any questions about what it is I'm saying when I talk about the real and imaginary part? Why sine and cosine are the real and imaginary parts of e to the IAT? Right, so if I want this and this, I calculate this and then just take real part and imaginary part. Here we go. The Laplace transform of e to the IAT is the integral from 0 to infinity e to the iat times e to the negative st dt, which is the limit. You need to be very careful with our limits here, because we're talking about limits of complex valued functions, limit 0 to r. Within the integral, I can combine these two exponentials as e to the iat minus st, which is e to the ia minus s times t. And now you see how easy the integral is. Everybody loves integrating exponentials. This is lim r to infinity 1 over ia minus s times e to the ia minus s times t. And this needs to be evaluated from 0 to r. The 1 over ia minus s is a constant, complex constant, but a constant. So he'll pop out at the evaluation step. And in fact, since it doesn't have any r's, the 1 over ia minus s comes all the way out past the limit. This is 1 over ia minus s times lim r to infinity, bracket, e to the parentheses ia minus s times r, minus e to the ia minus s times 0, which is e to the 0, which is 1. Now here's a limit to really cook your brain with. Complex numbers aren't ordered. There is no like this complex number is to the left of that complex number. In fact, they're two-dimensional objects. Complex numbers exist in the plane. So how the hell am I going to come up with the appropriate condition to ensure this goes to 0? So I'm going to pull something up here and we're going to do a little aside, little sidebar. Little side. Lim r to infinity, e to the ia minus s times r is lim r to infinity, e to the iar times e to the negative sr. The size of which I'm using absolute values here. There is a notion of absolute value for complex numbers. The absolute value of alpha plus I beta is alpha squared plus beta squared. You can think of it as the distance here's your complex number alpha plus I beta. You can think of it as the distance from the origin in the complex plane to your complex number, alpha plus I beta. And it behaves the same way as absolute value for real numbers works. In particular, it's multiplicative. So this is the limit as r goes to infinity, absolute value e to the ia r times absolute value of e to the negative sr. E to the negative sr is a real number. S is real, r is real, e is real. This is a real number. E to the iar is a complex number. And in fact, it's a complex number on the unit circle within the complex plane. This is cosine ar plus I times the sine of ar. So I'll actually write this out for you. This is lim r to infinity cos squared ar plus sine squared AR times the absolute value of the positive real number e to the negative SR. And the absolute value of a positive real number is that positive real number itself. So remember, absolute value of complex number, alpha plus I beta, is alpha squared plus beta squared. E to the IAR is cos AR plus I sine AR. So its absolute value is cos squared AR plus sine squared AR, alpha squared plus beta squared. And then the absolute value of a positive real number is that positive real number. Cos squared plus sine squared is 1. So this is lim r to infinity e to the negative SR. And this we know is 0 as long as S is positive. So those are the limit details for this guy. You can maybe begin to see why people get so into complex analysis, because it takes things that are otherwise extremely difficult and makes them phenomenally beautiful. The geometry here, like this thing, real quick, I'll go back. E to the I theta in the complex plane is on the unit circle. So again, this is the complex plane. This would be the number I, this would be the number 1, this would be the number negative I, this would be the number negative 1. And if theta is a real number, then this point right here on the complex plane is e to the I theta, because it's cos theta plus I sine theta. So e to the I theta is the unit circle in the complex plane. It's fucking beautiful. I just love it. Anyway, this piece goes to 0, this piece is 1, so this whole thing goes to 0 as long as S is positive, the condition we need for this, which means this is 0. As long as S is positive. This guy goes to 0 for all S greater than 0. Remember, S is a real number. So this is 1 over IA minus S times 0 minus 1, as long as S is positive, which is the negative of IA minus S, which is same trick as before, 1 over S minus IA. So what I need to do to get out the Laplace transform of cos AT and sine AT is to find the real and imaginary parts of this. To find the real and imaginary parts of this, I want to write it in that standard form of a complex number, alpha plus I beta. It's not like that. It's not even close to that. It's the reciprocal of something looking close to that. And the way you clean these up is by multiplying top and bottom by the complex conjugate. So remember how fractions multiply, parentheses, blah, blah, blah. The top is S plus IA. The bottom here, if you FOIL, you'll get S squared. And then plus IAS minus IAS, those cancel. And then minus IA times IA is minus I squared A, that's plus A squared. So this is S over S squared plus A squared plus I times A over S squared plus A squared. There you go. Real part, S over S squared plus A squared. Imaginary part, A over S squared plus A squared. So the Laplace transform of cos AT is the real part of this, which is S over S squared plus A squared. And the Laplace transform of sine AT is is the imaginary part of that expression, which is a over s squared plus a squared. And both of these work assuming s is positive. All right. So you know how to take Laplace transforms of sines and cosines, regular real exponentials, and any polynomial, and any linear combination of those sort of functions. Well, shit, that's pretty much all the stuff we see in this class. There are some other things, but you know, Laplace transform is pretty hard to calculate. I'm getting kind of tired of doing it. So I think that we should talk about a couple other things. So we can go on and calculate more Laplace transforms, but it's not worth it. You need one that's not on this list. Either calculate it or, you know, go try something other than the Laplace transform. Well, one of the things we do need. So when I go to use the Laplace transform to solve a differential equation, I'm going to take the ODE and I'm going to take the Laplace transform on both sides. The kind of built-in assumption there is that you can take the Laplace transform of y and y prime and y double prime, all the terms on the left-hand side that are to you unknown, right? I don't know what y is when I start solving my differential equation. My goal is to find y. But implicit in the procedure is taking its Laplace transform, which means I need to know under what sort of conditions I can take the Laplace transform of an arbitrary function or a generic function. If I don't know anything about the function, how do I guarantee I can take its Laplace transform? The answer is a growth condition called exponential type. So I want to share that rule. And then we're going to start talking about Laplace transforms of derivatives, because that's what we need to like dive in and take the Laplace transform of an ODE. Questions so far? So we're done just raw Laplace transform calculation. We're done. Questions on these? Where am I at with my time? All feeling pretty good? Okay, before we move on to the growth condition, I guess there's one other thing I want to say. If your function is defined piecewise, you all remember how to integrate piecewise functions, right? Laplace transforms, sorry, one more thing, piecewise functions. If f of t is made up of two other functions, well then f1 of t from 0 less than t is less than t naught, and f2 of t for t naught less than t less than infinity. You could split it up more than that, but let's suppose my piecewise function has two pieces. Then to calculate the Laplace transform of f, you have to split up the integral. So this would be, you know, integral 0 to infinity, f of t e to the negative st dt. I'm showing you this because some of the most important inputs, I mentioned this last time, inputs on the right-hand side are the Dirac delta function, which is like this kick unit impulse function, but it's weirdly defined, kind of piecewise 0 and infinity. The way you would do this is by integrating from 0 to t naught, this first guy, f1 of t e to the negative st dt, and then adding that to the integral from t naught to infinity, f2 of t e to the negative st dt. The same way you would integrate any other piecewise function. Now this this is not the Laplace transform of f1. Just be clear about that, right? This integral only goes up to t naught. So this is a regular definite integral. This is not an improper integral. This is not the Laplace transform of f2 because it doesn't start at 0. But this one is improper. So this guy would require a limit. This guy would not. So you have a homework problem or two like this. These are important functions. Like, for example, if you're going to turn a battery on and then take the switch off in a circuit, or if you've got someone like pushing on something and then eventually they're going to stop pushing on it. All of this stuff comes from like model of physical systems. And usually physical systems don't have inputs that go on and on and on forever. You smack the thing, you kick it, or you push it, or you have some force applied to it for some amount of time, but not forever. So usually one of the F1 or F2s would be 0. And usually the other one would be some reasonably well-behaved function, natural driving function, like a linear function, sine, cosine, exponential, something like that. Okay. Condition to guarantee the existence of the Laplace transform of f of t. So how do I know the Laplace transform exists if I don't know the function f? It's called, so that's just theorem. The Laplace transform of a function f will exist provided the kernel can drag it down fast enough. Remember, improper integrals, they only even have a chance of converging, kind of like infinite series. They only have a chance of converging if the thing you're integrating gets real small. If the function you're integrating is even constant, if you integrate a constant from 0 to infinity, that's infinite area. Even if it's really small, if it's constant, you've got a fixed finite height times infinite width, no matter how small that height is. If it's constant, that rectangle will have infinite area. The only way these functions have a chance is if they get small, if they eventually go to 0. Now, it's not f of t that needs to go to 0. It's the function you're integrating, which is f of t times e to the negative st. So if f of t itself goes to 0, that's certainly enough to guarantee that this integral converges, because the e to the negative st will drag it down. If f of t is a constant, that's enough to guarantee this integral converges, because e to the negative st, I mean, the constant would pop out, and the integral of e to the negative st will converge as long as s is positive. If the function f of t grows, like f of t equals t, or t squared, or t cubed, we've calculated Laplace transforms of functions like that. Those still exist, right? Those integrals still converge as long as s is positive to guarantee that this thing is decaying. So the condition is that f of t cannot grow faster than this can drag down. This term goes to 0 very, very quickly as a function of t for any fixed value of s. This goes to 0 very, very quickly. So the condition under which the Laplace transform will exist is that f of t cannot overwhelm functions of this sort. Now, the notation your textbook uses here, they say, do they say it? I know they have to have this. Yeah. So provided the function f of t in absolute value, his size, can be bounded above by some exponential. Call it m e to the ct. And it doesn't need to hold forever. And this is for some constants m and c, holding for all t bigger than some t naught. right? So as long as eventually your function gets dominated by some exponential, this integral will converge. That's the idea. This integral is going to, this function is going to drag you down so fast. The only way for this Laplace transform integral to fail to converge is if this guy overwhelms this guy, which would mean this guy would have to grow faster than any exponential. Because we've seen this, you multiply some other exponential in here, it combines with this, and the negative st in the power here will be enough to drag that shit down because t is going to infinity. As t goes to infinity, the negative st is going to go to negative infinity. So as long as your function doesn't grow faster than any possible exponential, the decaying exponential here will eventually win. Not every function f is like this. So some functions don't do this. But the good news is all polynomials certainly satisfy this, right? We know exponentials overwhelm polynomials. Any power function. But things that wouldn't work are like the gamma function. You cannot take the Laplace transform of the gamma function. You cannot take the Laplace transform of t to the t. You cannot take the Laplace transform of anything that grows way, way faster than any exponential. Oh, a fun example. So, for example, f of t equals any polynomial, power function, trig function, standard exponential, function which tend to constants, et cetera, et cetera, et cetera. Basically, all the functions you've seen in calculus satisfy this. Satisfy the condition above. Usually they call this being of exponential order, exponential type. It's a growth condition. Functions that don't satisfy this, f of t equals t to the t. F of t equals, how about e to the t? Kind of in the spirit of something we saw recently elsewhere. Gamma of t, right? F of t equals, I'll just write it as t factorial, why not? Really what I mean here is gamma of t plus 1. These are functions that are not of exponential type. They all grow too fast. These grow so fast that the Laplace transform for them would not exist. But the good news is solutions to linear constant coefficient ODEs generally are of exponential type. We generally can assume that the Laplace transform of those solution functions will exist, and therefore we are safe to say take the Laplace transform of those, even though we don't know explicitly what it is. So this is your growth condition. And it's called being of exponential type or exponential order. Another famous one, important one, f of t equals e to the t squared. That grows too fast. It doesn't even have to be e to the t, e to the non-linear growth power here would do the job. All right, I think that's enough of that. You can study the end behavior of Laplace transforms if you want. I'm not going to bother because all the ones we're going to work with, we work with explicitly. The other things we need to talk about are inverse Laplace transforms and Laplace transforms of derivatives. Now, in order to do any of that, we need to talk about partial fractions. So I think now is a good time to do a quick review of partial fractions. So we're moving into inverse Laplace transforms, but this is a prereq for inverse Laplace transforms. What do we mean by the inverse Laplace transform? Well, I mean, I give you the Laplace transform and I ask you what was the function that transformed into this. So I give you f of s and I ask you what is little f of t. I want to undo the Laplace transform partial fractions. You notice that the Laplace transforms of polynomials, exponentials, sines, and cosines are all rational functions, ratios of polynomials, right? Polynomials in S, like some number over S squared, some number over S cubed, or A over S squared plus A squared. Those are all rational functions. What the fuck do you do if I've got like several rational functions glued together and I want to pull them apart? So the beauty is that the Laplace transform being linear means its inverse transform will be linear, which means if you can kind of separate the pieces of the Laplace transform, I can go, oh, this looks like the Laplace transform of e to the t. This looks like the Laplace transform of t cubed. And then write down the inverse of each of those, and you've got your inverse. But you first need to pull apart the transform functions. You need to take your messes of s's and separate them into little neat things of s's. So here I'm going to use the variable s just for practice. I'm going to start by writing down a few inverse Laplace transforms just to give you some feels. So instead of going from f of t to big F of s via the Laplace transform, we want to go from f of s sort of backwards, and this is called the inverse Laplace transform, to little f of t. For example, we remember that the Laplace transform of 1 is 1 over s. So if big F of s is 1 over s, we know that comes from little f of t equals 1, i.e. the inverse Laplace transform of 1 over s is 1. Let's try another one. If f of s is 1 over s minus 2, we know that comes from, remember the Laplace transform of e to the at is 1 over s minus a. So this is 1 over s minus 2. So this must come from f of t equals e to the 2t, which can be, in the language of Laplace transform, Laplace inverse transforms, can be said the inverse Laplace transform of 1 over s minus 2, that's e to the 2t. I can do more, but I think you guys get the idea, right? So if you can take a function that is a rational mess of s's and split it up into individual pieces like 1 over s, 1 over s minus 2, then you can take the inverse Laplace transform of that rational mess of s's by individually inverting the little pieces. Now, how do you go from a rational mess of s's to 1 over s and 1 over s minus 2? That's the partial fractions. Turns out this is going to be a really important step. So let's see what we can do, eh? I'm not going to go back through all of partial fractions. For one, it's a pain in the ass to write out. For two, you memorize the cases, and then you sort of get to a place where you can feel your way through things. So suppose I want to decompose just going to show you some examples. The function 1 over s squared plus 3s. I'll call it f, big F, into nicer pieces. Just like you would do if you wanted to integrate this function. If I wanted to integrate this function, I would run partial fractions, split it up, and then integrate the bits. Well, here I want to inverse Laplace transform this function. So same idea. I want to split it up into nicer bits. Who remembers how to do this? Who remembers how to run partial fractions on something like this?
You factor the denominator.
Very good. So 1 over s squared plus 3s, that's equal to 1 over s times s plus 3. And because the two factors downstairs here are non-repeated linear factors, right? Those are the sort of cases. You've got non-repeated linear factors, repeated linear factors, irreducible quadratic factors that cannot be split into linear factors over the real numbers, although you could do it with complex numbers. And then in the nightmare case, you've got repeated irreducible quadratic factors. But in the nice case, non-repeated linear factors, you assume that this can be written as some constant over the first factor plus some other constant over the second factor. And like goddamn everything in this class, we're leaning heavily on linear algebra here. The fact that this can be done, let me write it. The fact that this can be done is a fact from linear algebra. It's equivalent to linear independence of powers of s. From here, we need to sort out the constants a and b. Right? If I know a and b, then I'm Gucci. I've split this up into two pieces. Each one I know how to take the inverse Laplace transform of. Bunch of ways to do it. I think the way that is most digestible without being very slow is to cross multiply by that denominator. So I multiply both sides by s times s plus 3. On the right hand side, I'll have a times s plus 3 plus b times s. Insert joke here. All right, because the s's will cancel here. When I multiply this by s times s plus 3, the s's cancel, and you just get a times s plus 3. The s plus 3's will cancel here. If I multiply this times s plus 3, the s plus 3's cancel, and just the s remains. And now send s to 0, you'll get 1 equals a times 3, or 3a, plus 0b. So a has to be 1/3. And send s to -3 to get 1 equals, let's see, a times 0 here now, -3 plus 3 is 0, plus -3b, which implies b has to be -1/3. Okay, therefore, what have we learned? 1 over s times s plus 3 is 1/3 over s plus -1/3 over s plus 3. And now if I want to take the inverse Laplace transform of my function, hence the inverse Laplace transform of 1 over s squared plus 3s is equal to the inverse Laplace transform of 1/3 over s plus -1/3 over s plus 3. And remember what I said, if L is linear, then L inverse is linear. Yet another fact from linear algebra. So this is 1/3 times the inverse Laplace transform of 1 over S minus 1/3 times the inverse Laplace transform of 1 over S plus 3. That's 1/3 times, what is the inverse Laplace transform of 1 over S? We said it above. Whose Laplace transform is 1 over S?
1.
1. Minus 1/3 times the inverse Laplace transform of 1 over S plus 3. Whose Laplace transform is 1 over S plus 3? Think carefully of this one.
E to the negative 3t.
Very good, right? 1 over S minus A is the Laplace transform of e to the AT. This is 1 over S minus negative 3. So that's e to the negative 3t, i.e., given f of s equals 1 over s squared plus 3s, we know that little f of t, I'll factor the 1/3 is 1/3 times 1 minus e to the negative 3t. Boom, you just took your first inverse Laplace transform. So, where am I with time? Yeah, we're about there. So, in the future, here's what we are going to do. I will discuss inverse Laplace transforms for all the functions whose Laplace transforms we just found. You just read the table backwards. I will show you how to take the Laplace transform of a derivative. The way we will use these to solve differential equations is to take the Laplace transform of both sides. On the left-hand side, we will be taking Laplace transforms of a bunch of derivatives. On the right-hand side, we will be taking the Laplace transform of your input or driver function. On the left-hand side, we'll write the Laplace transform of those derivatives as, capital Y of S. And on the right-hand side, we'll end up with other rational functions of S. We will then invert the Laplace transform to recover the original function little y. So when you take the Laplace transform, your differential equation is going to become an algebraic equation, or system of algebraic equations, maybe. You then solve those. Turns out initial conditions are important here. It kind of only works for initial value problems. Then you solve the algebra problem, invert the Laplace transform, and you get your solution function out. It's incredibly slick. But the procedure requires some kind of meta-analysis. You want to think about it quite carefully. So you've got plenty of homework to be working on. I strongly encourage that you practice taking Laplace transforms, that you try to get comfortable with the linearity conditions and all of that. Next time, I will show you how to solve some differential equations using the Laplace transform. From there, we're going to go on to look at some sort of special properties, shifts and unit impulses, things like that. But then we'll be done with the Laplace transform. So it's a very cool machine. You need to be good at partial fractions because inverting the Laplace transform is a crucial step in the solution process. So if you haven't practiced partial fractions in a long time, be a good idea. Be a really good idea. As always, Patrick JMT, Paul's online notes are great resources for that. That's it. That's all I've got for you guys today. Any questions before I let you go? Okay. Then I hope you guys have a lovely rest of your day. Work hard. If you need help, as always, just ask. I'm here. Office hours, Canvas, email, whatever. I'll see you tomorrow.